So in this video, I'm going to cover some supplementary material for topic 1 in module 1, which will include the derivation of the energy equation for open channel flow and also the application of the principle of conveyance to compound channels. So firstly, the energy equation for open channel flow, which is down here. And this is derived from the Bernoulli equation, which you will have encountered before in your fluid mechanics course. And the Bernoulli equation states that for a small parcel of water, for example this parcel here, travelling at velocity d at height y above the bed with pressure py, the total head, which is the sum of the velocity head, the pressure head and the static head, is a constant along a streamline, which is the path that parcel takes through the water. To get the energy equation for open channels from the Bernoulli equation, we need to take the average of these terms and bring them to the energy equation. Now the average of the velocity term, v squared on 2g, is in fact u squared on 2g if we assume that the velocity is constant over the cross-section. For these two terms, the pressure term and the static head term, we can consider these two together. It makes things somewhat easier. Now the pressure head term varies from 0 at the surface to d at depth d, the bed of the channel, and it varies linearly. In contrast, y varies from height d at the surface to height 0 at the bed, and again varies linearly. So the sum of these two terms equals d at any point in the cross-section. It's constant. So the average value is d, so we include that in the energy equation, and we need to include z, the height above some arbitrary datum as well. So for the energy equation, these three terms, the velocity term, the static term, the potential term, and these sum to a constant along the channel if you include the height z above the stream bed, above the arbitrary datum. Just one final thing and a reminder, and you would have covered this I'm sure in previous courses, the units for each of these terms is meters. Okay, so their head and their units are meters. To convert them to energy terms, or more precisely energy per unit volume, you have to multiply by rho g, the density of water times the gravitational acceleration. Okay, next I want to talk about the approach referred to as conveyance for estimating discharge, and we'll apply it to a compound channel. But first of all, let's think about a simple channel which just has a fairly straightforward geometry. Now to estimate discharge for a known water level, we can calculate that using the product of cross-sectional flow velocity times cross-sectional area. So we can write that in this way, velocity times area. And we can estimate velocity using Manning's equation, which we have here, and so we have this term here. And we can rewrite that as conveyance times slope to the 1/2. You can see slope to the 1/2 here. If we let conveyance, K, equal cross-sectional area to the 5/3 divided by Manning's roughness coefficient times wetted perimeter to the 2/3. Remembering that the hydraulic radius is equal to cross-sectional area divided by wetted perimeter. The beauty of conveyance is that it's only dependent on the geometry of the channel for a given water level. It's not affected by flow velocity, and it's not affected by gradient. And this is helpful when we're estimating discharge for more complex channels like this one, which is a compound channel. This is a typical compound channel where we have a main channel and a floodplain channel, and in this case 2 floodplain channels, 1, 2 and 3 are the 3 compartments that we use to model this compound channel. To estimate discharge in this compound channel, all we need to do at this particular water level, all we need to do is to calculate conveyance for each of the three compartments, K1, K2 and K3, for this water level. And in this case, the wetted perimeter is just the boundary of the channel. It doesn't include the interface between the two compartments. This assumes that there's no momentum transfer across the compartments. There's no shear acting at these boundaries. So anyway, we can calculate this conveyance for the three compartments at this water level, and if we multiply each of those by the stream gradient and add them, we get discharge for the whole cross-section, and that's what this equation says here. The beauty of this approach is that we can calculate conveyance for multiple water levels, and we can calculate it once, and we can then estimate discharge at all those levels once we know what the stream gradient is. This makes things easier when we're doing some hydraulic modelling using the gradually varied flow equations, which we're going to talk about later on, in particular in topic 3, where we deal with backwater calculations. But for now, this simplifies the task of handling complex channel geometries in compound flow when we're estimating discharge.